Hi chemistry. I hope you are preparing well with our courses. Here in this video, we are analyzing JAM 2019 chemistry problems. So watch the video completely to get detailed conceptual analysis of each and every problem. Okay, right. The correct option for the number of bending modes of vibration in each of H2O, CS2 and SO2 molecules respectively. So before going to answer for this problem, we are going to check some concept on it. We know that 3n minus 6, okay, 3n minus 6 gives number of fundamental vibrational modes of a molecule, that is of a non-linear molecule, okay, and 3n minus 5 gives number of fundamental vibrational modes of linear molecules. But here in this problem, we need to find bending modes of vibration. For this, we need to use 2n minus 5 for non-linear molecules and 2n minus 4 for linear molecules. Okay, now we need to look at the geometries of the given species or molecules. Water molecule is non-linear. We know that, and for that we need to use 2n minus 5 formula, and here n indicating number of atoms present in that molecule. Here we have 3 atoms, 1 oxygen, 2 hydrogens. So 2 into 3 minus 5 resulting 1. So water molecule has 1 bending mode of vibration. Now just look at CS2. We know that carbon disulfide is a linear molecule. For that we need to use 2n minus 4 formula, and we have 3 atoms in it. 2 into 3 minus 4 resulting 1. So CS2 produce 1 bending mode of vibration. Now SO2 molecule is non-linear molecule. That's why 2 into 3 minus 5 resulting 2. Okay, sorry, resulting 1. Okay, now SO2 producing 1 bending mode of vibration. So 1 to 1 is the correct answer, and option D is our answer. Okay, right. And next question. The total number of degrees of freedom of an HBr molecule that is constrained to translate along a straight line but doesn't have any constraints for its rotation and vibration is. So here already we have explained this problem in a particular video, so where we have given complete conceptual analysis on it. Just check that video in your course. Okay, right. Next one. According to the kinetic theory of gases, the ratio of the root mean square velocity of molecular oxygen and molecular hydrogen at 300 Kelvin is. Okay, so here we need to have command on important velocity formulas. Okay, here we need to look at root mean square velocity. We know that root mean square velocity as under root 3 RT by M. Okay, here R indicating constant, gas constant, and T indicating temperature in Kelvin, M indicating mass of that particular molecule. Now just consider O2 molecule. For that, 3 into 8.314 into 300 Kelvin, because we have given with 300 Kelvin temperature, by what is the mass of molecular oxygen? 16 plus 16, that is 32. Okay, right. And now just for H2 molecule, 3 into 8.314 into 300 by 2, because H2 mass is 2. Okay, so from that we can get almost 15 is 60, so we can get 1:4. Okay, just check 1:4 in option C. That's why option C is our answer. Now just check, just have some extra information. We know that most probable velocity equals to under root 2 RT by M. Just remember it. Now here average velocity equals to 8 RT by pi into M, under root 8 RT by pi M. Okay, just remember these important velocity formulas. Next question. The half-life time of a chemical reaction A to P for initial reactant concentrations of 0.1, 0.4, we have 250 seconds respectively. The order of the reaction is, so what you understand, the half-life time T of is decreasing by increasing initial concentration of A. Okay, so this is the relation you can see from the given information of problem, and we know that T half, okay, so T of equals to 1 by K under root, sorry, the concentration, initial concentration of reactant. So it is for second order reaction. So from this relation we can say option C is our answer. Okay, just remember, for second order reaction, half-life time increases whenever concentration of reactant decreases. Okay, or whenever concentration of A or initial concentration of reactant increases, then half-life time decreases. Now just check or just note important relations here. We know that T half is directly proportional to initial concentration of A, okay, for the zero order reactions. Okay, and the T off doesn't depend on initial concentration for first order reaction, because just look at here, T half equals to, so the initial concentration of A by 2K for zero order reaction, and we know that T off equals to 0.693 by K for first order reaction. Okay, just remember all these important equations. Now next question, the ratio of the nearest neighbor atomic distances in body center cubic BCC and F center cubic FCC crystals with the same unit cell edge length is. Okay, now so here we need to look at the radius of that cubic cells, okay, BCC and FCC. So that is the distances we need to find. So for BCC, okay, body centered cubic crystal structure, we know that the radius is equals to under root 3 A by 4. For FCC, it is so simply under root 2A by 4. For simple cubic, it is A by 2. Okay, and just remember, for diamond, it is under root 3A by 8. Okay, now we need to look at the relation between or ratio between BCC and FCC. Okay, so under root 3A by 4, okay, 3A by 4 into here 4 by under root 2A. Okay, so simply we can get under root 3 by 2. Now just check, option A is our answer. That's it. And next question, the correct trend in the rate of substitution of Cl minus by pyridine in the following complex is. So we have given with trans effect problem. Okay, right, now just look at here, we need to look at these ligands, right, because so this is the leaving group, that is the chlorine is the leaving group, and we need to look at the trans effect of these ligands. Okay, now just try to look at the concept lecture in your course. And now for this problem, just check it. We know that sigma donating ability of ligand and pi accepting capacity of ligands increases trans effect of ligands. Okay, now here all the given 4 ligands, or so simply we can say sigma donors and chlorine pi donor also. Okay, whatever, but the strength we need to consider the stronger donating ability, that is sigma donor ability. When we look at sigma donating ability, hydride is has a strongest sigma donating ability. Okay, and followed by CH3. Okay, CH3 minus, followed by C6H5 minus, followed by Cl minus. Okay, this is the order of a strong sigma donating ability, right? So whenever strong sigma donating ability increases, trans effect increases, that is the bond to the trans of these ligands weakens. Okay, this bond will become very weak, that's why easily the chlorine can cleave from it. So that's why the rate, okay, the rate of substitution of Cl is highest for 4th option, because the highest trans directing or trans effect is for hydride ligand. Okay, now 4th one here. Now second should be for methyl, that means the complex which is having methyl ligand trans to this chlorine leaving group. So the second highest rate for first compound. Okay, and now we need to look at second and third, in which is having C6H minus 5, so that is third should be there. Here is a 3. Okay, now 4 and 1, now 2. Okay, 2 here and 3 here. So option A is the correct answer. Okay, right. And next question. In qualitative inorganic analysis of metal ions, the ion which precipitates as sulfide in the presence of H2S in warm dilute HCl is. Okay, now here's you need to look at some important information of metal ions and which are going to dissolve and how we can separate them in a qualitative way. Okay, now just check some of them. Most important metal ions: copper plus 2, bismuth plus 3, and cadmium plus 2, mercury plus 2, arsenic plus 3, stibinum plus 3, and tin plus 4. All these metal cations produces insoluble sulfide ions. Okay, so they can be precipitated by adding high amount of sulfide ions. So that is simply acidic solution of H2S, hydrogen sulfide. Okay, whenever you add acidic solution of hydrogen sulfide to all of these metal cations, they will be precipitated and they can be separated from that liquids, that means solution. Okay, right. And next group we can see here: silver plus 2, Pb plus 2, mercury plus 2. Okay, so they will produce insoluble chlorides. Okay, so whenever we add HCl to these metal cations, they will produce precipitates. Okay, that means they will be separated by adding HCl. Now just look at the next group of cations. Here we can say aluminum plus 3, Cr plus 3, Fe plus 3, zinc plus 3, and here zinc plus 2, now nickel plus 2, and cobalt plus 2, manganese plus 2. All of these metal cations produces a slightly soluble, okay, slightly soluble sulfide ions. So they can be precipitated by adding basic solution of H2S. Okay, so just to check the differences here. Okay, so all of these metal cations can be precipitated by adding basic solution of hydrogen sulfide, whereas all these metal cations can be separated or precipitated by adding acidic solution of hydrogen sulfide. Just check the differences. Okay, now we can see magnesium plus 2, calcium plus 2, and strontium plus 2, and barium plus 2. All of these metals, okay, all of these metal ions can be precipitated by adding carbonates. Okay, so that's why after doing these things, by just separating all of these metals by adding H2S, acidic solution of H2S as a first step, in the second step by adding HCl, and third step by adding here basic solution of hydrogen sulfide. Now if we add carbonates, we can precipitate magnesium plus 2, calcium plus 2, strontium plus 2, and barium plus 2 from the solution. That means we can separate them. Okay, now just remember Na plus, sodium plus, K plus, and NH4 plus, they cannot be precipitated with any of above reagents here, that is hydrogen sulfides, and here as we take an HCl. So whatever the reagent which we have used on all of the given metal cations, so they cannot precipitate Na plus, okay, NH4 plus, and potassium plus. Just remember them. Right, now just check the options. In qualitative inorganic analysis of metal ions, the ion which precipitates as sulfide in the presence of H2S in warm dilute HCl is. Okay, here warm dilute HCl. So in warm dilute HCl, we can simply precipitate here sulfide in the warm, that means in acidic conditions. Okay, so in acidic conditions, chromium plus 3, bismuth plus 3 can be precipitated, and all of them, cobalt plus 2, aluminum plus 3, chromium plus 3, can be precipitated in basic solution of H2S. Okay, right, that's why our answer is option D. And next question here, The correct statement regarding the observed magnetic properties of NO, O2, B2 and C2 in their ground state is, okay, right. Now just check here. To give answer for this problem, we need to look at the molecular orbital diagram, MOT, okay, right. And we know that for less than or equal to 14, okay, less than or equal to 14 electron species, we can use this kind of molecular orbital diagram, whereas for more than 14 electrons we can use this one, okay. So just check it right now. So 2 here, 2 here, 2 here, we can fill like this, okay. Now just check NO. In NO, nitrogen contributing 7 electrons, oxygen contributing 8 electrons, so total 15 electrons. Just fill up them. So 2, 4, 8 and 9, 10, 11, 12, 13, 14 and 1 electron here into anti-bonding orbital. So 1 electron is there, that's why NO is paramagnetic in nature, okay. Now just come to B2. So B2, each boron contributing 5 electrons, so total of 10 electrons. So 10 electrons will be filled up here, okay. So 10 electrons will be here, 8 here, then 9 and 10. So you can see unpaired electrons in bonding molecular orbitals, so it is also paramagnetic in nature, okay. For molecular orbital more than 15, you should use this one, okay. So for NO, you need to use this molecular orbital diagram, okay, right. Just remember that. Now for C2, we have total of 12 electrons, right. So 12 electrons, just fill up till 2 here, we have 8, now 9, 10, 11 and 12. So you can see a paired electrons, all of paired electrons can be seen for that C2. So C2 must be diamagnetic in nature, right. Now just check the options. Now next one here we have given with O2, molecular oxygen, which is having 16 electron, each oxygen contributing 8 electrons, okay. Now fill up. So till 2 here we have 8 electrons, now 9, 10 and 11, 12, 13, 14, 15 and 16. You can see in anti-bonding orbital, molecular orbital, we have unpaired electrons. So O2 is also paramagnetic in nature. Now NO, okay, NO, O2 and B2 are paramagnetic in nature, and here C2 is diamagnetic in nature. Just check it, okay, right. And next question, the observed magnetic moments for octahedral Mn+3, iron +3 and cobalt +3 complexes are given 4.95, okay. So just check it, 4.95 and 6.06 and 0 Bohr magneton respectively. The correct option for the electronic configuration of Mn+3, Fe+3 and CO+3 metal ions in these complexes respectively is, okay. Now just check for Mn+3. Here we have 4.95. So we can just check here. If we have 4 unpaired electrons should be there. If we have 3 here, 3 point something, then 3 unpaired electrons should be there. If we have 2, so 2 unpaired electrons must be there. If we have 5 point something, 5 unpaired electrons must be there, okay. So right, and now so just check it here for Mn+3, okay. For Mn+3 it is 4.95, so it should contain 4 unpaired electrons. Now you can see T2G3 Eg1, okay. We have given with octahedral diagrams here, okay, octahedral splitting energy levels. In T2G we have 3 unpaired electrons and Eg we have 1, so total 4 unpaired electrons, resulting 4.95 Bohr magneton for manganese +3. Now just look at iron +3, so which is giving 6, okay. So for that 6, right, and for that 6 we need to look at that means it must have 5 unpaired electrons. So here in T2G 3 unpaired electrons, and in Eg we should have 2 unpaired electrons, okay. High spin nature should be there. So for that T2G3 and Eg1, okay. Now just check for cobalt +3, it is 0 magneton, that means zero unpaired electrons must be there. Okay, so for cobalt plus 3, right, for cobalt plus 3 we have D6. Okay, so 6 electrons must be filled up in the T2G only, then only all the electrons will be paired up. Okay, now you can see, so no unpaired electrons, that's why zero magnetic moment for that complex. Okay, now just check here, we need to have T2G6 and EG0. Now it is completely fulfilling option C, right? So option C is our answer. So just you can find the answer by just checking the number of unpaired electrons, no need of the formula. Okay, right. Now next one, among the following compounds, the one having the lowest boiling point is, okay, so here we know that the general trend is carbon tetrachloride here, silicon tetrachloride, germanium tetrachloride and tin tetrachloride. Okay, so the general trend from silicon to germanium, boiling points increases, whereas the boiling point of carbon tetrachloride is more than silicon tetrachloride. Okay, so in the group of tetrachlorides of group 4, the lowest boiling point for silicon tetrachloride. Okay, so whenever we move down in a group, we know that the size of the metal, the silicon to germanium and germanium to tin increases. Okay, the size increases, and which leads to increasing the size of molecule. Then we can say the van der Waals interaction forces increases between the big sized molecules. That's why here we can expect high boiling points whenever we move down from silicon tetrachloride to tin tetrachloride due to increasing van der Waals forces between the molecules. Okay, right, here carbon tetrachloride is having highest boiling point when we compared with silicon tetrachloride. Okay, so here all of them are just at room temperature will be observed as liquids, and why silicon tetrachloride will having lowest boiling point. So just try to check it. Okay, it's an assignment for you. And in the next video we are going to check all other questions of JAM 2019. Okay, 2019 chemistry. Thank you very much. And if you are interested, just visit and join chemmasters.online for best concept oriented courses. Thank you very much.